Hi, thank you, Sarina, for the very nice introduction. I want to introduce to you my current project, exchanging water molecule in protein-ligand free energy calculation by Monte, Carlo molecular dynamic sampling. So as we all know, binding free energy is easy to calculate from molecular dynamic simulation. We just calculate the difference between the protein-ligand complex to the components separate in solution. As long as our cavity is solvent exposed, we don't have a problem. If our cavity is buried, we'll find ourselves in a situation similar to this, which is obviously wrong, and where we want to be is here, where water occupy the cavity. So the solution we did is we performed translational water moves with Monte Carlo, which allowed buried cavities to be hydrated and dehydrated. To speed up the calculation, we define a steric grid where gray represents the atoms, dashed line the hydration shell around them, and everything that is covered by an atom or the hydration shell is considered inaccessible for water. That means we are trying to place water only in areas that are free. This results in us needing to perform a lot less energy calculations. Another optimization we performed, we focus on an interest in an area of interest. What does it mean? We don't really care about water exchange between bulk to bulk. This is kind of sampled very well in the molecular dynamics. We care about what happens in the protein-ligand complex within the interior. So we trim our simulation, our grid for the Monte Carlo from the 3 direction. We did extend it in the 1 axis into the Z. We did extend our grid for the Monte Carlo into the Z axis to allow some bulk water to exchange, because we assume that the first and second hydration shell water might be more difficult to move. So we kind of extended it into the bulk. And the way we did it is we just implemented our Monte Carlo code into the Ember MD package. It's available already since Ember 18, also in the current Ember 20. A bit about the outline of our program. We perform n number of MD steps. Then we enter our program marked in blue. We build the steric grid. Then we choose a random water and a random destination. We calculate the energy and perform the Monte Carlo criteria. If it is rejected, we just go to the next step. If it is accepted, we update the coordinates of the water molecules and the coordinates of the grid. And then we keep on doing this until we reach the predetermined number of MC steps. Once we reach this number, we go out again and perform the MD. In order to check that our method is working, there are 2 criteria we have to obey. First of all, we need to allow water molecule to exchange in and out of buried cavities. And 2, we want to yield a correct Boltzmann distribution. So we created a very artificial system with 2 graphene walls that don't allow water to penetrate. If we perform MD, obviously nothing happened. If we perform MCMD, we can see that water can cross the barrier and occupy the middle region. If we're looking at this graph, red is the density in the outer region, blue is the density in the inner region. We see that densities go up and down correspondingly until they equalize between the 2 regions. The next thing is a thermodynamics test system, which we built, again, a very artificial system, low density water, 500 K, which is pretty much steam. The purpose of this system is to have a very high acceptance rate for MC, because if we generally just try MC, the acceptance rate is so low, it can be within error range. In our current system, our acceptance rate is about 45%, which is a lot, which means the MC has a significant impact on the total energy. And what we could see is very nicely that red is the energy of MD, Green is MCMD, averages are the same, distribution is the same, everything looks good. So this is kind of our previous paper. We published it in 2019. The conclusion of this part is that MCMD is able to place water molecules in a thermodynamically correct manner in solvent inaccessible cavity, and the number of water molecules can change during the simulation. The fact that it is thermodynamically correct leads us to our next step, which is this allows us to use our method in binding to energy prediction, which is the next step. So as we all know, binding to energy, as said, we calculate the difference between the protein-ligand complex to the components. And in a classical thermodynamic cycle, we just do a relative binding to energy. We convert ligand 1 to ligand 2, but the difference is that this perturbation results in the change of the hydration state. In order to test the ability of our method to be used in binding to energy calculation, we built a data set that we had 4 requirements. 1, we want to have a buried cavity. 2, to have at least 2 similar inhibitors. 3, to have different number of buried waters between the different ligands. And 4, we need to have experimental data for these ligands. So let's have a look at one example. Ligand W1, we convert it to ligand W2, changing the hydroxy to methoxy results here in the displacement of these 2 water molecules. And the way the pipeline, or the way we did our calculation, we did it, the perturbation in 3 steps: decharge, van der Waals, recharge, brackets, the number of windows, or the number of lambda windows in each step. We calculated both directions. So we convert ligand 1 to ligand 2 and ligand 2 to ligand 1. And we repeated the calculation 5 times. This pipeline is taken from Silicon Therapeutics, our collaborators in the project. We see here, of course, the perturbation from the one direction will be exactly the inverse of the perturbation in the opposite direction. Now, the graph is a bit busy, but let me take you through it. So we performed 4 different methods. We start in all of them from the protein-ligand crystal structure. For methods 1, 2, and 3, we remove the crystallographic water, we solvate and set up the window, and then for method 1 and 2, we perform an equilibration using MCMD. In this equilibration step, everything is restrained except for hydrogen and water molecules, which means that if needed, the water molecules can occupy their place in the buried cavity. Then we performed for method 1, TI using MCMD. For method 2, we do TI using only MD. Method 3, we did the equilibration using only MD. So if the cavity is inaccessible, the water molecules cannot go in. And then we did the TI using MD. Method 4 is a bit different. In method 4, we kept the crystallographic water, and then we performed everything the same. What does it mean? It means that if we are converting ligand W1 to W2, we will start with these 2 water, and in the opposite direction, we will start without these water molecules. The take home, or what we want to remember from this slide, methods 1 and 2 are MCMD, method 3 and 4 are only MD. And this kind of leads us to the point of this method, because if we are converting in different lambda windows, at some point, or the windows are of course independent, and we want to place the water molecules, but we don't know how many to place. So we start from ligand W1 and we end at ligand W2. On the left is the number of water molecule at the end of the equilibration step, averaged over the 5 simulations. And this is kind of, again, the important point, because we see the first and last window might be easy to tell because we know that we need to have 3 and 1, but we see that we don't really know what to do in the middle windows and how to determine the hydration state in each of the windows. So we kind of let the MCMD do it. And here, when we look at the results, we see that we start from around 3. And along the simulation, we go down and end at about between 1 and 2. On the opposite direction is the window of W2 to W1, which is projected in the opposite direction. So we just see the exact same number of water. A dashed line represents the standard deviation, and the numbers are just the averages. If we are looking at the right, we see here is a running average of the number of water molecules during the TI window. And we see that the numbers during the TI windows are very similar to the numbers at the entrance to the TI window. So the equilibration step pretty much determines the number of water molecules. It can change slightly later, but this is kind of the important part that determines it. Another important thing, why is this important? Because we could have cases of partial water density, especially in the middle windows where water could be equally favorable in and out of the cavity. The fact that we're repeating the calculation 5 times, we assume that in such a case, the repetition will represent it, and in some of the cases, the water will be in, and in others, the water molecule will not be in. And in the total average of the energy, this will be taken into account and lead to correct calculation. Now for the results. First of all, as always, we check the hysteresis of the perturbation. This is a very fancy equation, but if we go back here, we just see that we kind of sum the two numbers. If the value is 0, it means that the hysteresis is 0 and the simulation works very well in both directions. It just means that both directions get the same value. And this is very interesting because what we can see is that methods 1, 2, and 3, not completely surprisingly, kind of expectedly, leads to very low hysteresis. It means that the back and forward simulations are very similar. These are the 9 perturbations we had in our data sets. Not very surprising, method 4 leads to very high hysteresis because, as we said, we start with different number of water for each direction. So it kind of creates a mess, and this leads to very high hysteresis. And now let's see how we work with relative binding free energies. So then we compared our numbers to the experimental data. Here it's also very interesting to see that methods 1 and 2, which are doing MCMD both, are kind of similar and have very low values, around 1 kcal per mole. Method 3 and 4 are both not doing well, with RMSEs of 3 to 4, kind of high, kind of not succeeding. There are a few very interesting things to see here. First of all, if we look at the specifically W1 to W2 in method 3, so the hysteresis, I'm back one slide back. If we're looking at the hysteresis was 0.0, but 7 kcal, almost 7 kcal difference from the experimental value. So the back and forward were very similar, but completely wrong in both directions. So just looking at the hysteresis is not enough. Another thing that is very interesting, that if we're looking, many of the simulation, even if we don't consider the water molecule at all, work quite well. And this is actually this is in agreement with literature, where it was in multiple cases shown that water does not need to be taken into consideration, which is kind of strange and not very intuitive. But if we think about it, if a water molecule is equally happy in its cavity and in bulk, then taking this water into account does not necessarily matter for the relative binding free energy calculation. So this is very interesting to see that the source of the error is from a few perturbations that fail miserably. Method 4 again leads to high numbers. This is from our last paper, which was just accepted last week, and it is currently in press. It's not yet online. Now there are a few things I wanted to show or focus about. When I checked the structure of the HSP90 for FCQ, there are in the crystal structure 3 buried water molecules, 1, 2, and 3. When I simulated my program, I very consistently only occupied 1 and 2, and water molecule 3 was never occupied. Looking at the electron density, or what we see here, we can see that water molecules 1 and 2 has a very clear and defined electron cloud representing them, whereas water molecule number 3 has it looks like a contamination on the ligand, because it seems like just something is growing out of the ligand. So maybe a contamination in the ligand resulted in electron density here that resulted in placement of water molecule. So speaking with the crystallographic friend, they told me something like, as a crystallographer, I don't care if I'm putting water in or not, it doesn't matter for me. And I'm like, okay, for me, it can kill my calculations. So that's a very big deal for us. So it's always kind of another advantage of using our program, that we kind of just trust ourselves and not add any additional source of error to our calculations. So this is very important. Something else that I wanted to discuss, we had another perturbation that we determined as an outlier, and I want to show it because I think it's very interesting. So the KEK, it's a tripeptide, glutamic acid changed to tryptophan, and we see that whereas experimental value is 0.1 kcal per mole, the all 4 method resulted in about 15 kcal per mole error. So there are 2 main reasons that could cause for such wrong numbers. One is if we are not placing the water molecules correctly, and 2, if the TI calculation is just not working. So what we did is we checked, first of all, how our water placement looked in compared to the crystal structure. Pink is the crystal structure. Here is when the first lambda windows of the KEK to KWK mean it's still fully glutamic acid. And on the right is the last window of the opposite direction perturbation, means again, it's fully glutamic acid. And what we see is that the water molecules are very perfectly placed, nicely overlapping. Looks like the water placement works well in this case. On the bottom is the opposite direction of the perturbation of tryptophan to glutamic acid. And again, we still see that 2 of the 3 water molecules are very correctly placed. One is not exactly placed, but looks close enough, to be honest. And this leads us to think that the water placement succeeded, and the problem is not the water placement, but probably some kind of force field issues. Also, the fact that all 4 methods fail in a very similar way leads us to think that it's not an artifact or a fluctuation or something. It's a very systematic error. Probably our guess is the force field.
Sorry, so, 1 minute left.
Perfect. So to conclude, MCMD samples the hydration of buried sites in a thermodynamically correct manner, and it was successfully used for relative binding free energy calculation, resulting in low hysteresis and high agreement with experiment. With that, I want to thank, first of all, the collaboration from the first project, Charlie, Lynn, Ross Walker, and Tom Kurtzman, which led us to the next collaboration, which I would like to thank Shishon Lin, Charlie Lin, Brian Raddak, and Woody Sherman from the amazing collaboration in silicon therapeutics. And of course, my PI, Mike Gilson, and the entire Gilson group for an amazing environment. And with that, I want to thank the committee for inviting me and you guys for listening. Thank you very much.
Thanks a lot, Ido, for the nice presentation. So we have a couple of questions, and I was asked to read also the names of the people that asked the questions. So the first one is from Debarati Dasgupta. And the question is it absolutely needed to do 5 or more than 5 TI runs to have enough confidence in our simulations? You specified 5, so was there that an arbitrary choice? Also, for absolute free energy calculations, how do we assess the convergence of the TI runs?
So I tried 5 just because one, it was the pipeline that Silicon Therapeutics usually used. I wanted to make sure that I'm kind of consistent. I did not see huge differences between the 5. So I cannot say 5 is enough, 5 is not enough. I guess it's very much system dependent. So if the system fluctuates, it might not be enough. If the system is relatively stable, it will probably be enough. So this, I just did not try less. For absolute binding free energy, it's kind of more problematic because what I saw, I actually started doing it, and what I saw is that most absolute free energy cases result in, so I did see that our program was able to properly place the water, but I did not see an influence on the absolute free energy. So I don't know how to say, so this is something we are still checking. I cannot say how to best do it for absolute free energy.
Okay, thanks. Then the next question is by Jacob Littman. Have you found any advantages to method 1 versus method 2? Using the MCMD solvent placement only as an equilibration step makes it easier to incorporate into other workflows.
We were thinking about it. To be very honest, I did not see huge advantages for method 1 over method 2. I think, again, the starting, if we start with the correct water placement, then we will be doing good. So to be honest, the results of methods 1 were better than method 2, but I would say within error range. So I would say if we are doing the equilibration step, it's probably sufficient.
Okay, thanks. Then we have a question by Niels Hansen. Very nice approach. I have 2 questions. What is the ratio between MC trial moves and MD steps in between the MC phases? Is the orientation of the water molecule optimized in the MC insertion?
So the orientation is not optimized in the MC. The reason for that is we kind of assume, since we choose random water, the random water will have random orientations. And then once they are placed, they can optimize themselves in the MD. So the MC will just be to place them. So we did not account for orientation of the water molecules in the placement. And as for the ratio, in this step, the MC is significantly more than MD. I think I did 100,000 MC to 100 MD, but the MD here is pretty much meaningless because just for, again, hydrogen and water. And in the next step, I did it 10 to 1, so 10 times more MC than MD. But again, I did not try to optimize the method. It was more as a proof of concept that it's working. So I kind of did a lot of MC steps on purpose. I think it can be reduced, it can be optimized, especially with knowing the system. Kind of, if you know, this we have found in our previous paper that kind of we had the major urinary protein and the cytochrome C peroxidase, that the difference in the hydrate in the buried cavity required in the CCP 10 times more steps than in the MUP. So accordingly, if we know the system, we can account for it in the relative binding free energy. Here, all systems were kind of blind to me, so I just did it very extensively.
Okay, thanks a lot. So in the interest of time, we can unfortunately not do additional questions, but there are additional ones in the Q&A. So please, Ido, if you can afterwards answer them directly in the Q&A. So thanks again for the presentation. And then if you can stop sharing, we would move on to our third speaker of this session. So let me introduce Max Ebert. So Max, can you share maybe already your screen? So Max studied bioengineering at TU Dortmund and at the Kyoto University in Japan. He did his PhD in biochemistry at the University of Montreal, in 2016. And since 2017, he is an application scientist at CCG in Montreal. So Max, the floor is yours.
Thank you. Actually, it's pretty funny because most of the time when I give a talk, I'm the last slot of the day. So I don't know what it means, but I hope everybody still has some energy to go through the last talk. So I'm Max, as I was just introduced. I work for CCG, and I wanted to share our adventure to implement the thermodynamic integration method from Amber in our software Mo. So yes, so as we heard many times today, so the goal of free energy calculations is obviously to predict absolute relative free energy of bindings, which is super interesting and useful for drug design and lead optimization. And you basically apply this to a series of compounds, which makes this approach kind of complex to set up. So our goal was to basically come up with a platform which allows everyone to use free energy calculations. So absolute free energy of binding, we heard that multiple times today, we cannot achieve other than going to the D. Shaw research group, I guess. But the relative free energy of binding is much easier to calculate if the ligand binding mode is similar, and if the ligands have a somewhat similar substructure, but we will get to that a little bit later on in the talk. So typical methods, we saw MC and MD today, and we talked about free energy perturbation and thermodynamic integration. And there's a long history in the literature on all those methods, but since in 2018, the Amber Group released TI for GPUs, we really saw that there is now a possibility to, oh, by the way, I could share maybe my video so that people can see me. So basically, when they released in Amber 2018, the GPU support for TI, we thought that now the pharmaceutical industry can really benefit from this sort of calculation. So really briefly, the TI approach basically doesn't go the direct route where you have a protein and a ligand in solution and then measure binding and unbinding events. But it takes advantage of the thermodynamic cycle and basically does the alchemical transformation of ligand A and the binding pocket to its counterpart ligand B over the course of various different MD simulations. And this is done in the context of the binding pocket, but the same alchemical transformation is also done in the unbound state. So this transformation is an integral. So this integral we cannot solve directly. So we introduce in this field the lambda interpolation variable and use then numerical integration to solve the integral. So the basic idea is that these two ligands, ligand A and ligand B in the binding pocket, they have some sort of common core, which might be large or small, but these are atoms shared between the two ligands. And then obviously we have a group which is disappearing and appearing, so that from the point of view of the protein, you only see fractionally ligand A or ligand B, while the two ligands, they don't have any interaction from a non-bonded perspective. So numerical integration can be done through very different means. So, but essentially what we try to do is to get the relative energy of binding by choosing different lambda windows to evaluate the average energy at each point to then solve the integral. So if you have here on the y-axis the energy and on the x-axis the various different lambda windows, we could imagine here at lambda 1, which is at about 10%, maybe ligand B, and 90% of the non-bonded terms of ligand A would be seen from the protein perspective. And so you can either do this equally spaced, and we heard about the equally spaced issue a little bit earlier from the colleague at Cresset. But what we do here in Mo, we use a Figure's quadrature, essentially, which is a really interesting numerical integration scheme because it overemphasizes and oversamples the edges of the lambda transformation, which is historically quite challenging and has a lot of errors. So it is quite suitable for this type of analysis. So all what matters in the TI run essentially is the soft core potential. These are the non-bonded terms, which we tone down by varying lambda. So we basically reduce the Coulomb term and the van der Waals term accordingly during the alchemical transformation. However, they do not reduce at the same rate. So we introduce an alpha and beta parameter in the soft Coulomb potential of amber to basically tone down the strengths of the Coulomb term, because otherwise it will overtake the repulsive strengths of the van der Waals term, and we will see a lot of singularities. And up to amber 18, these values were set to alpha 0.5 and beta 12. So why is this interesting? It's because when we started the project, we essentially saw a lot of instability in all our TI runs. So we thought, okay, let's invent an easier system than the multi-body system. And so what you see here below is a two-particle system where we basically measured the average separation, or the distance between the two particles, if we vary the lambda value for one of the two particles. And so we have here at the top, the lines in green to gray are basically repulsive terms. So the charge is repulsive, and you see that when you tone down the lambda value, so basically make one of the two particles disappear, they sit as 10 angstroms for the repulsion, and then when you come to a full disappeared particle, you are around Brownian motion on average. Since these are now really simplified MD simulations, we can actually record here 10,000 different TI runs. So that is actually pretty interesting because it makes it pretty accurate. When you see the neutral transformation, it sits around 6 angstroms. And then over the course of the lambda transformation, we go then to also Brownian motion. However, when we have an attractive force, either minus 0.5 up to -2, at the beginning, when the two particles are fully there and the force field is the regular force field, we have a distance similar to a salt bridge. But when the soft Coulomb potential in amber kicks in, we quickly see singularities. So essentially, we have nuclear fusion because the Coulomb term takes over and can overcome the repulsive force of the van der Waals term. So we identified this as one of the main issues because when you have now these 10,000 points, you nearly describe the integral completely, but it results into high curvature when you have nuclear fusion. And with numerical integration in TI, you will never be able to accurately describe this integral with such a high curvature of the integrand. And this also leads to high variance. So when you bring this to a macroscopic world, let's say, where you have a full protein system, here the T4 lysozyme example from the AMBER website, where the phenol ligand is a non-binder and the benzene ligand is a binder. When you look at the relative binding energy between the two, even if we increase the number of lambda windows, we can never stabilize this relative energy of binding, even if you extend the simulation length of each lambda window up to 10 nanoseconds. So there is a clear problem in the soft Coulomb potential. So now that we have this easier two-particle system, we can run lots of optimization simulations. And so in our last release from last year, we then published the alpha 0.2 and beta 17.3 values for the soft Coulomb potential because they completely mitigated the van der Waals collapse of the charge systems. And so in the meantime, the AMBER group also identified this as a problem. And in the AMBER 20 release, they also addressed these alpha and beta parameters and optimized them accordingly. So when you now compare the optimized alpha beta parameters and do a full 10,000 lambda window scan and compare this to numerical integration using 6, 8, 10, or 12 lambda windows, you see that starting from like 9 or 10 lambda windows, you essentially have zero error or difference between the numerical integration and the full exploration of the integral. So when you bring this back to the example I showed before of T4 lysozyme, now independent of the simulation length for the simple system, starting from like 9 or 10 lambda windows, you see a stable delta delta G for the benzene to phenol transformation. So we were really happy. And then we moved on to basically identify what is necessary for workflow so that everybody can set up a free energy run. So obviously you need to start opening a crystal structure of a protein-ligand complex and then make an all-atomistic model out of it. And for that, Mo already has all the necessary tools on board. So if you're familiar with our software, you might have seen Quick Prep in the past, which is an automatic workflow to prepare protein and ligand structures. Or you can also manually prepare the structures like with our Protein 3D and structure preparation application. So that was already implemented in Mo. Next step is ligand placement. So you need a method somehow to bring in the ligand in the binding pocket. And for that, we also have already a lot of different tools on board. You can either build the ligand manually in the pocket or use our docking application to do template force docking using fragment tools or like a standard SPDD approach. So that was also already covered. The part we did not have was identifying pairs. So the moment you are having more than 2 ligands you're interested in simulating, you basically need to set up a simulation plan, which ligand to transform into which, so that we can get the absolute relative binding energy of the entire series of compounds. And then also we needed a system to basically create the bound and the unbound state of the identified pairs, generate Amber input files so that they can run independently from Mo on a large HPC cluster, and then needed an analysis part to interpret the data coming back from the Amber TI run. So let's look at the simulation planning. So simulation graphs are there to actually not only predict the absolute relative energy of binding, but also to reduce error. So we add redundant edges to create cycles, which allows for error detection, minimization, and correction. And these edges are actually chosen by heuristics or topologically similarity. And when we look at the literature, common topologies are usually suboptimal because they are representing trees with complex branching where people by topological similarity are clustering ligands together and having 1 or 2 connectivities to another cluster. So if one of those 2 connectivities then fall apart for any reason, the entire network is falling apart. So it's a little bit like having a really good internet in North America and Europe, but basically connecting both just by a single cable. If it's cut, well, then the whole network falls apart. So we went into the literature on network research and said, okay, every transformation will have a certain error, but the error will be on a similar order of magnitude. So which allows us to actually simulate all different sorts of topologies. So for example, when you look at the path topology, and here on the y-axis, you have the expected error, and on the x-axis is the size of the graph, the longer the graph gets, the more edges you have to traverse, and you are basically collecting error after error after error. So that is not a really good graph. That is maybe quite logical, but also when you look at the ring at the beginning, it's actually a really good graph because you have only a couple of steps for each ligand, and also you have a cycle closure analysis capabilities, but quickly the ring becomes so large that you're getting closer and closer to the path topology. A pre-calculated topology, which is often used, is the star topology, because you only have 1 step for each ligand in the graph. However, you have no error correction potential. So what we first used was the fan topology, which allows basically for pre-calculated topology, which is near optimal for the simulation resources, and you have cycle closure for all the ligands in the system. However, what would be ideal is the complete path, because then you have the most information and your network is the most stable and can actually have some failed connection points because it will be resurrected by the entire network. So what we came up with at CCG is an optimization function, which interpolates the optimal graph between the star and the complete graph based on the computational resources you're willing to invest. So how much GPU time you're willing to invest per ligand. So how does it look like So every time when you add a new edge, you get a lot of information on the entire series of compounds. So what we will prioritize using our optimization function, which is shown here in the bottom left corner, is to spend all the simulation time the user defines to create more edges in our network. And these edges are actually chosen randomly, but having equal connection points for each ligand. This works for us well because we are not using a maximum common core analysis like most implementations of free energy calculations. We actually use a minimal common core analysis, which has 3 to 4 atoms which are shared between all the ligands. So the vast majority of atoms are actually transformed. So it is independent of any chemical similarity, which also allows us to do charge transformations and ring opening and closing transformations. So basically, adding an edge is always advantageous. But if there's no simulation time left to add a new edge, we then use the remaining simulation time to try to add a new lambda window. With our initial optimization calculations, we saw that below 11 lambda windows, there is basically no simulation stability to be achieved. So since our interface is steered towards a regular user, non-expert, there is no way to fall below 11 lambda windows. However, if there's enough simulation time left, we can increase the number of lambda windows, and that's done automatically. So this allows us for an extra stem point on the numerical integration. The least bang for the buck, let's say, to reduce errors, actually making the actual lambda window simulation longer, because that only averages the energy over a longer trajectory. So that's why this is the least of our priorities, and that's where the remaining simulation time will be placed. So why is not everybody using free energy calculation in the industry? Is because it's hard. So we really need to go through a lot of steps and use a lot of arcane syntax and shell scripts to run a single TI transformation. So we need to read the PDB file, we need to protonate the system, we need to create parameters for the ligands and for the protein, we need to identify the core, the ligand placement has to be done, and then we need to set up each individual simulation for the lambda windows, run it, and then analyze it. So there's a lot of expertise which is necessary. And so in the Mo implementation, we try to strip away all the complexity of the setup process. So we have a Streamline interface, which allows us through the already known tools to create a full all-atomistic model of the protein-ligand complex, place the ligands in the binding pocket based on the assumed binding mode, and this doesn't need to be perfect. So once we identify the ligand pairs, the superposition on the common core, on this minimal common core, is done automatically for the user. So then you have essentially our panel, which allows you to control things like simulation length or the simulation resources you want to invest. And then finally, when you issue the scripts, it generates a fully self-contained shell script which supports workload managers like Slurm, SGE, and LSF. And so you can run it on an AWS cloud or your in-house HPC, but you can also run it locally on your graphics card. So there's basically nothing you have to do. And in our new Ember 2020 release, this can also be done directly from the GUI interface. So you can submit an Ember run on your cluster via the graphical user interface. So we, as I said, generate automatically all the input files necessary for the TI run. Here, especially, there's no Mo involved anymore once these input files have been generated, so it's entirely Ember. So everyone who knows the Ember MD engines will feel really familiar. The way we set this up is that the ligands will first be calibrated in the mean field to create an average structure, which will be then used to individually seed each lambda window, which makes it a really efficient scheme to run this on multiple graphics cards. And you also do not have any issue with hysteresis.
Max, sorry, one minute left.
Yes. Once you have the simulation done, we then read in the results and present them in our Mo interface. So we predict the absolute relative binding energy, and you can also, based on the error prediction, either remove some edges or individual ligands. And you can also look at all the energy distribution at each lambda window. One analysis which was really helpful for us was the autocorrelation function of the energy, because basically what you want in each lambda window is to pick a random sample, and the autocorrelation of that will be noise-like. However, if you do a transformation and you have structure in the autocorrelation function, then you actually do not have a reach equilibrium. What you see here, that is a benzene to benzene transformation, and that's really important because since we have the minimal common core, we can do these transformations of self-transformation, because at the beginning of a project, that's the only relative energy of binding we know, which is essentially 0. So you can use that to benchmark if your system is suitable for free energy calculations, because as we've seen today, if we are honest to us in our field, is that you cannot expect more than 50 or 40% success rate for free energy runs for different systems. So you want something noise-like. If you have identified some problem, you can rerun the individual lambda window and get some noise-like lambda window to resurrect your transformations. Finally, just one benchmark quickly. We ran the P38 map kinase example like everybody else. And for these 5 ligands, we get really good agreement between TI and FEP+. We also always calculate a single point molecular mechanics interaction energy, because we really want people to not jump directly the free energy calculation ship. We really want people to use the best and fastest method. And so we express the MM all the time. If you have experimental data and that is already correlating, you should stop and not run free energy calculations at all. Just quickly here for the different topologies. So we analyze the same TI run with like the ring topology, and has basically no correlation. The star topology in this run had no correlation, but if we use the fan topology, it had correlation, which was reasonable or started to be reasonable. And then if you use the fully optimized path, but based on what I described, we on the full P38 map kinase set. So any method, TI, FEP+, or even the single point molecular mechanics interaction energy, they all scored the same for the P38 map kinase set. So a really quick summary. This is all integrated since Mo 2019, but also was enhanced in Mo 2020. We support Amber 18 and Amber 20 as the platform. You do not need any Amber tools. The force fields and the charge models are all done in Mo automatically, and which makes it really easy for anyone to use it, even for non-experts. And so thank you for your attention, and I hope there are still some people left to ask questions.
Thanks a lot, Max, for the nice presentation. So we have a couple of questions. The first one is from Debarati Dasgupta, and the question is, how many trials and runs were performed before you arrived at alpha equals 0.2 and SC beta equals 17.3? Are these parameters highly sensitive to the system type?
Yeah, so we optimized this on a 2-particle system. So we randomly changed alpha and beta. We had multiple minima. And to be conservative, we chose the smallest minima for alpha and beta, or which was the closest to the originally published alpha and beta values. So like in Amber 20, for example, they used the same alpha value we came up with, but they have a slightly larger or beta value of beta 50. We have one of the minimas at beta 50.5, but we didn't use it because we were not sure. Nobody ever varied alpha and beta since the Amber group came up with the soft co-potential. So we didn't want it to be too extreme. So we ran multiple thousand simulations, but since it's only 2 particles, that is pretty quick and can be done on a laptop in like an hour or so.
Okay, thanks. Then we take one more question, and that's from Noor Kalous. Great talk, Max. Did you try calculating the free energy using other estimators than TI, like bar or M-bar? Because according to the literature, bar and M-bar are better than TI or 20.
No, not at all. We only focused on the optimization of the TI protocol. And we really try to push the TI method in and itself by choosing a really tiny core, which actually helped us to identify, and we collaborated with the Amber group, and also we had a vivid exchange with Silicon Therapeutics on that, which really helped us to identify the problem with the nuclear fusion and to pinpoint the main issue on the soft core potential. So our main interest is to make the TI method better. We are not looking into the other methods right now. We felt really strongly about doing the direct path to minimize the number of TI runs necessary for decharge and recharge calculations, to parallelize the TI setup by running individual lambda windows independently from each other. So that was where we mainly focused on.
Okay, great. Thank you very much, Max, again for the presentation and all the speakers in this session. So there are a couple of questions in the Q&A, so please, if you still have time to answer them. And also there are actually some new ones for Ido, so if you could also still answer them, that would be great. Kira or Hannah, do you want to kind of say something for tomorrow?
Sure, I can go ahead and do so since I think Hannah's still recording. So thank you all today.